Hi all, welcome to this third lecture of dynamics and controls of linear systems. Today we'll discuss about stability of linear systems. But before getting started, let's look at what we discussed in the last few lectures. So we discussed, we introduced what a linear system is and how can we write about its dynamics. So here the dynamics of a linear system is given by x dot equals to ax, where x is some n cross 1 vector and x is the state of the system, and a belongs to is the n cross n matrix. Now the solution of such a linear system can be given as xt e to the power at into x naught, where x naught is initial condition or initial state of the system, and e to the power at is just a matrix, which is a shorthand for the Taylor series expansion of exponential, in which you replace x with at. Now this can be written, e to the power at can be written in a easier form or more intuitive form like this: t e to the power dt t inverse into x naught, where d is the diagonal matrix in which diagonals are the eigenvalues of matrix A, and t is the eigenvector matrix of the matrix A. Now the benefit of this is if D is a diagonal matrix, e to the power dt is also a diagonal matrix in which each diagonal term goes to the power of exponential. So in this way we can easily represent what is a solution of e to the power dt. So t e to the power dt t inverse is a simplified representation of the solution of the linear system. Now moving ahead, we'll look at the stability, or how can we look at the stability of a continuous system. So continuous system can be represented by the dynamic equation x dot is equal to ax, where x is a n cross 1 vector and a is a n cross n matrix. Now for looking at its stability, let's look at its solution, which we have already seen: e to the power dt t inverse and x naught. Now if you look here, the only term that is dependent upon time is e to the power dt. The rest of the terms are constant. So as time increases, this is the only term that changes, and it is at this term that the stability of the system is dependent. So we'll look at e to the power dt. Now e to the power dt, as we saw previously, can be written as e to the power lambda 1t, e to the power lambda 2t, e to the power lambda nt. So if it's easy to see that if any of these diagonal terms goes unbounded or goes to infinity, then the system becomes unstable. So let's say if t tends to infinity, if all of these terms are bounded within some range always, then the system is stable. But if some e to the power lambda it goes to infinity as t tends to infinity, then the system is unstable. Okay, so let's see what this instability means. What is e to the power lambda it? So okay, let me change this lambda it to lambda kt, because that was a little bit confusing. So lambda kt tends to infinity. Now, so what does lambda some e to the power lambda t means? So as we all know, lambda is the eigenvalue of a, and it can be represented as a plus iota b, so where a plus is a complex number, lambda is a general complex number. So if lambda is a plus ib, what is e to the power lambda t? It can be written as a plus ib into t, which can be further written as at cos bt plus I sine bt. So this is the Euler formula. We are using Euler formula to represent e to the power ibt. So let's look at it in deep. So e to the power at cos bt plus iota sine bt. As you can see, the amplitude of this term is always 1. So it cannot go beyond 1. Alright. So the state is, so e to the power lambda t can go unbounded only if this e to the power at goes unbounded. Now, which means if a is greater than 0, then e to the power at tends to infinity as t tends to infinity. Correct? So if a is greater than 0, then that xkt will grow unbounded. Okay, and hence the system will be unstable. If a is less than 0, then e to the power at tends to 0 as t tends to infinity. Correct? In that case, the state decays the state decays to 0 as t tends to infinity. Okay, so in this case, the system is unstable. In this case, the system is stable. So summarizing our above discussion, we can say that if real part of eigenvalues of A is greater than 0, then system is unstable. And this is for any eigenvalue. So even if one of the eigenvalues is greater than the real part of one of the eigenvalues is greater than 0, then the system is unstable. Now if we say real part of all the eigenvalues of for all eigenvalues of A, then system is stable. If it is less than 0, then the system is stable. We can also represent this in the form of a graph. So let this graph represent the eigenvalues of A. Okay, so the right half of the plane, if the eigenvalues lies here, then the system is unstable. If it lies on the left half of the plane, then the system is stable. So in general, it can happen that for a system, some eigenvalues are lying on the left and some are lying on the right. So what do we do with the control is we try to bring these eigenvalues from the right hand plane to the left hand plane using BU. This is what is the control of the system means. Now continuous systems are good stability of continuous system we discussed. But now sometimes it happens that we we want to analyze some discrete system. That is, let's say, because in real life we observe a system at specific instants rather than continuously observing the states. So the models generally we have are discrete models. Okay, so let's look at the stability of discrete linear models, or stability of discrete systems. So let's assume x dot is equal to ax is some continuous system which is represented in discrete terms as, which can be represented in discrete terms as xk plus 1, which is basically state at k plus 1th time instant, is given by some a tilde. This a and a tilde are not same. We'll discuss what is the relation, times the state at kth time instant, where xk is literally the state at kth time instant, and where this is like step time. Delta t is that in time instant at which we are observing the state. So this is time instance. Okay, so first, moving forward, we just want to look at what is the relationship between xk plus 1 and a tilde and a. So as we know, for the continuous system, the solution can be written as e to the power at x naught. So in the same way, so actually a tilde is e to the power a delta t. That's what it is. And even though we'll not use this relation in determining the stability of this discrete system, but it's good to know what actually the relation between a tilde and the actual a of the system is. Now, moving ahead, we'll see how the system progresses as time progresses. So let's say we have some initial condition x naught, and we have some a tilde, or dynamics of the system a tilde, and at the first time instant we get a new state x1. Okay, what is the state at time instant 2? So it is same as a tilde dot x1, which can be written as a tilde square x naught. Correct. In similar way, we can write a x3 equal to a tilde cube x naught. Basically, this is the relation between initial state and the x and the state at in time instant 3. In a similar way, at nth time instant, we can say the relationship is a tilde to the power n x naught. Okay, so this is our relationship between initial condition and the nth time instant, and the state at nth time instant. Now, previously, like we have seen in a little bit of linear algebra, we've previously seen that any square matrix a tilde can be written as t d t inverse. Let's call this t tilde d tilde and t inverse. So this is eigenvalue decomposition. And it's very basic linear algebra stuff. You might think, oh, where did this come from? So it's very easy to look. So we have that characteristic equation in which we write ax is equal to lambda x, where lambda is the eigenvalue of a tilde and x is the eigenvector. Now you convert this equation to matrix form, which contains all the eigenvectors and eigenvalues. So you can write it like this: a tilde t tilde equals d tilde t tilde and d tilde. So take a moment to see that if T is a eigenvector matrix, that is each column vector is each column is a eigenvector, and D is a diagonal matrix in which each diagonal element is an eigenvalue, then this is true, and this is same as this equation. So once you get hold of that, we can just convert the sequence equation to A tilde is equal to T tilde D tilde T tilde inverse. Okay, we can write it like this. Now why I'm doing is, like, I want to, so if I know A tilde, how do I calculate A tilde to the power n? So let's say I want to calculate A tilde square, which I can write it as T tilde D tilde T inverse T tilde D tilde T inverse T tilde inverse, and as you can see, it comes out to be D tilde square T tilde inverse. I hope you can see this in one step. So A tilde square is actually this, and similarly you can prove A tilde to the power n is equal to T tilde D tilde T tilde inverse, where D tilde is to the power n. Okay, so this is what we can write, and so we'll put this equation. So A tilde to the power n x naught is equal to x n, correct, which can be written as x n equal T tilde D tilde to the power n T tilde inverse x naught, where D, the only term that is changing with time steps is this D tilde to the power n step. Rest of them are constant, and where D tilde is nothing but lambda of A tildes. So it's basically eigenvalues of A tildes. It's a diagonal matrix which contains, whose diagonal elements are the eigenvalues of A tildes. So this is what D tilde is, and if we raise it to the power n, and the property of diagonal matrix is that the diagonal values will raise to the power n. So basically, if any of these values, same as previously, if any of these values goes to infinity or goes unbounded, then the system is unstable. And if all of them dies out or are bounded as n tends to infinity, then the system will be stable. Okay, so let's look at one of the eigenvalues, lambda to the power n. So if this goes to infinity as n tends to infinity, then system is unstable. But if this is bounded as n tends to infinity, then the system is stable, correct? Now let's see, and where lambda is eigenvalue of A tilde. Okay, yeah. Now lambda can be written as A plus IB, or will not write it as A plus IB, but any complex variable can be written as in polar form as e to the power r e to the power iota theta. So this is the good thing about complex numbers, that it can be represented in polar coordinates also. So let's say this is r raised to the power iota theta, where this is theta. Okay, so this is real axis, this is imaginary axis. So any complex number can be represented in these polar coordinates. Now if we raise eigenvalue to the power n, we raise the absolute value to the power n and e to the power iota n theta. So you realize this is this just gives you the angle of the complex number. It's actually this value that is increasing its value. So we can and this actually, what will happen is, if we represent it here, the theta might change, and theta, but it will go, actually the absolute value is what will make it unstable. So based on this analysis, we can say that if r is less than 1, then the system is stable, and if r is greater than 1, then system is unstable. Okay, now let us look at it in a graphical perspective. So if r is less than 1, so this is a unit circle. So if r is less than 1, then system is stable. So if we have a A tilde matrix such that its eigenvalues are all inside this circle, then we can say that the system is stable. If any one of them is outside this circle, then we'll say that they are unstable. Okay, so I'll just write it stable and unstable. Okay, so this is the slight difference between discrete and continuous system, in which in continuous system the right half plane is the unstable part and the left half is stable, while in discrete systems it's a unit circle inside which everything is stable and outside which everything is unstable. So that is the analysis of and for the analysis of the stability of a linear system. We'll meet in the next lecture. Till then, thank you and goodbye.